Hello everyone, in this calculus and engineering tutorial we explain how to calculate the sphere volume by using an integral. And here's the problem that we want to solve. Consider the sphere with a radius of r. By using integration calculus and integrals, show that the volume of the sphere is v is equal 4 over 3 multiplying pi multiplying r to the power 3. But before we start with explanations, let's explain the importance of this problem. Namely, in this problem, and by solving this problem, you will learn how to calculate the volume of a solid by using integrals. And the solution will be very elegant. So let's start immediately. Here's an illustration of the main idea for solving this problem. First of all, if we slice the sphere by the plane xy, we will obtain this circle. The radius of this circle is r. In this representation, the z-axis is oriented toward you, and you will only see the tip or the top of the arrow of the z-axis. And I will denote the z-axis like this. Next, if we slice the sphere by a plane that's parallel to the yz plane, and if we slice it over here, in this plane, this slice will look as a line. That is, the projection will be like this. However, in reality, this slice is a sphere. And this sphere is represented by this dashed ellipse over here. Let us assume that this slice actually has the width of dx. And obviously, the distance from here to here is y, and the distance from the origin to this point over here is x. That is, what we did over here, we simply sliced the sphere, and as the result we obtained this disk. Of course, the curvature over here is not completely flat. However, if the dimension is infinitesimally small, then it will be a straight line as an approximation. Okay, so let's continue. This point over here has coordinates x and y. Since this point belongs to this circle, it should satisfy the equation of the circle. Consequently, since the radius of this circle is r, we will have that x squared plus y squared is equal to r squared. From this equation, we obtain that y squared is equal to r squared minus x squared. And over here, we will only take the positive y values. Consequently, y will be equal to square root of r squared minus x squared. However, we will only need this form. And again, over here we are only taking the positive branch, we are not taking the negative branch. To summarize, we concluded that this value y is actually equal to square root of r squared minus x squared. Next, let's calculate the area of this circle over here. That is, this circle over here is obtained by slicing a sphere by using a plane that's parallel to the plane zy. And what's the area of this circle? Obviously, the radius of this circle over here, that's actually represented by an ellipse, is radius squared multiplying pi. And obviously, this y value depends on x. This means that this area over here will be a function of x. Consequently, we write a, that is the area of this circle over here, is a function of x, and it's equal to pi multiplying y squared. Next, let's substitute this value over here. We obtain that the area of this sliced over here is pi multiplying r squared minus x squared. Our goal is to compute the volume of the sphere. And moreover, the task is to express the volume as an integral. So let's learn how to do that. The volume of this disk over here is obviously the area of this disk, that's equal to A of x multiplying dx. So we can write like this. dV, which represents the volume of this small disk, is simply equal to A of x multiplying dx. Now, the volume of the sphere can be segmented into series of infinitesimally small width disks represented over here. That is, we can simply slice the sphere over here, over here, over here, over here, and there will be an infinite number of these slices. The volume of every slice is equal to dV, that is, it's equal to A of x dx. Then, the volume of the complete sphere is equal to an integral of dV, where dV over here depends on x, and over here we will substitute the bounds later on. Okay, so let's substitute this expression over here, and let's see what do we get. We obtain V is equal to, first of all, let's just write an integral, and later on we will figure out the bounds. We will have A of x dx. For every fixed value of x, we have a slice, and we will have slices starting from minus r to plus r. Consequently, over here the bounds are from minus r to plus r, and this is very important. And consequently, this integral becomes, if we substitute the expression for A of x, it becomes an integral from minus r to plus r, and over here we will have pi multiplying r squared minus x squared multiplying dx, and that's it. Let us compute this volume integral. Volume is equal to, first of all, let's split this integral into two parts. The first part is an integral from minus r to plus r over here. Then we will have pi r squared dx. Then we will have minus over here, an integral from minus r to plus r over here. And let's see what we will have. We will have pi multiplying x squared multiplying dx. Let's evaluate the first integral. The first integral becomes pi r squared. Integral of dx is simply x, and we will have the bounds. The bounds are from minus r to plus r. And let's evaluate the second one. We will have minus sign over here, then we'll have pi, and we will have x to the power 3 over 3, and let's not forget the bounds. The bounds are from minus r to r. Good, let's continue. So our volume becomes pi r squared, and over here we have r. Then what do we have here? We have minus r. And then let's see what do we have over here. We have minus pi over 3, and let's substitute the bounds. Let's see what do we have. The first bound is r to the power 3, then we'll have minus, and over here we will have minus r to the power 3. Good. Let's continue. So the volume becomes pi r squared multiplying 2r over here. Then we have minus pi over 3. And let's see what do we have over here. Over here we have r to the power 3, then minus, and we have minus r to the power 3. This is again minus r to the power 3, so we'll have 2 r to the power 3. So let's nicely write it. Here it is. Perfect. As the result, we will have over here 2 pi r to the power 3, then we will have minus 2 over 3 pi r to the power 3. Consequently, we will have, in the denominator, we will have 3 over here, and over here we can write pi. Let's see what we will have over here. We will have 6 r to the power 3 minus 2 r to the power 3. And consequently, our volume becomes 6r to the power 3 minus 2r to the power 3 is 4r to the power 3. Consequently, we have 4 over 3 r to the power 3 multiplying pi. And that's it. That's exactly the very well-known formula for the volume of the sphere. And from this example, you can learn the power of mathematics and power of integrals. You can do amazing things with integrals, and you can prove almost any volume formula if you can segment the shape into smaller pieces and then you can integrate them. Okay, that's all for today. Thanks for watching this video.